All right, three types of collisions. We have perfectly elastic collisions where mechanical energy is conserved. Objects bounce, no energy is lost. So this is mechanical energy or total energy. All right, our final energy after a collision is equal to all the energy we had before a collision takes place. In the momentum, mass times velocity. So obviously the momentum is conserved too. If the v is transferred from one to the other, then you have this this taking place. Now this happens that you could see it. So obviously, when you have these same masses. Now we have perfectly inelastic. This is where two objects stick together, and some energy is lost. And what happens here is momentum is conserved. So you conserve your mass-velocity relationship. Your final momentum is equal to your initial momentum. And we have an example here of railroad cars. When they hit each other, they lock. They bump and lock. Yep. Inelastic collisions. Objects bounce, but some energy is lost. Momentum is conserved. So in all systems, momentum is always conserved. All right. All right. We have a 14-kilogram toddler. He throws a 0.38 kilogram football, 4.7 meters per second to the right. Find the recoil velocity of the child. So you have a child with a football, throws the football.
He moves back.
All right, good. And what is that? And how do we find that? All right, so we have our final momentum is equal to our initial momentum. He's standing still initially, so our initial momentum is 0 because our initial velocity is 0. All right, so our final velocity is we have a kid who's moving at a speed, and then we have a football that's moving at a speed. The child is 14 kilograms. The football is 0.38 kilograms, and the football is moving to the right at 4.7 meters. All right. Our final velocity is equal to our initial velocity. Pi is 0. Pf is our two objects' momentums. All right. We fill in the numbers. We separate our variables. And
wait, why is that equal 0?
It equals mass times velocity, right? Right?
What?
Momentum. Mass times velocity?
I'm talking about at the thus part.
This part?
Yeah, and why is that?
Oh, because this is all this stuff.
Yep.
Is equal to this, which is 0.
Oh,
so
okay.
all this stuff equals 0.
Oh, yeah. So
Right. This is PF on this side, and this is PI on this side. All right. And once again, we see that this is negative, which means that if positive is to the right, negative is the velocity to the left. Okay? Yes?
Yeah.
All right, so we have an 8-ton rocket traveling at 3 miles per second. After firing engines, rocket mass drops 7 tons, and it travels at 5 miles per second. Has momentum been conserved? But we got mass times velocity,
Well,
engines
yeah,
fired,
momentum
mass
is
times
conserved.
velocity.
Momentum's always conserved.
Good, momentum's always conserved. All right, so we have yes, momentum is always conserved. All right, we have 8 tons, or our final one is 7 tons times our final speed is miles per second. So 7 times 5 is not equal to 8 times 3. So why? What happened here?
Wait. Well, you're going too fast.
Okay. All right. Okay. All right. Okay. All right.
Is this?
What's missing? Why? If this says it's not, if our final momentum is not equal to our initial momentum with these numbers, what's missing?
Energy? I guess I'm confused.
All right. We're missing, yeah, you're confused. That's it, right there. We dropped some fuel. Don't forget the exhaust gas. How much did we lose?
A ton.
We lost a ton of exhaust fuel. So our final momentum is not just the rocket ship. It's the rocket ship and the fuel. We lost a ton of fuel, and the fuel itself was thrust with a velocity. And we can solve out, all right? We have 8 times 3 minus 7 times 5 divided by 1, and we get negative 11 miles per second for the exhaust gas's velocity.
Where's the second question?
It's not there.
What?
So the question is yes, and I showed you why.
Oh, and just don't. Wait, so what does that have to do with the second part? What is that? Is that explaining why they're not
Oh,
equal?
yes. Because you had a question here, didn't you? You wanted to know why. So this is the answer to your question. All right? Okay, so next question, we have train car A has a mass of 25,000 kilograms and initial velocity of 5 meters per second to the right. Train car B has 15,000 kilograms initially at rest. Cars collide and couple. Find the velocity at which the cars move off together. Right? So here we have before, here we have after. Once again, we saw perfectly elastic. What would these be? What type of collision would this be?
Inelastic.
Perfectly inelastic, because they actually stick together as one mass afterwards. All right, so there's our momentum before. We have mass and velocity of both cars. Here's the momentum after, which is the mass of both cars with one velocity together. They're equal to each other. All right, so here we have mass times velocity of car A, which is moving, and we also have mass and velocity of car B, which is at rest, but at rest means 0. So mass times velocity equals 0. So this added to car B only gives us the momentum of car A, and it's equal to our final momentum, which is both masses added together, and we want to know what that velocity is. So we divide this answer by 40,000 kilograms, and we get 3.1 meters per second to the right.
Wait, what did you divide by 40?
We're looking for this. All right, so divide this side by 40,000.
Oh, you divided the other side by 40,000. All right.
Divide this side by 40,000.
Yeah, I got it.
And we get 3.1 meters per second. All right? You cool with that?
Yeah.
All right. Is kinetic energy conserved? Yes or no?
Yeah.
No.
Oh, what the hell?
Because remember, we got that written down.
Well, not all of it's conserved,
Uh,
but some of it is, isn't it? Because heat's lost.
well, conserved means everything. You save it all.
Oh.
ME isn't conserved for perfectly inelastic collisions. So you want me to show you? Yeah? All right, so we have, this is before. we have our initial kinetic energy is of both trains, right? But one train's not moving. Its velocity is 0.
What does ME? Oh, mechanical energy?
Yeah, mechanical energy.
Alright.
So our initial kinetic energy is 1/2 mv squared of car A plus 1/2 mv squared of car B. Car B is 0, so basically we're stuck with just car A, and that's 3.1 times 10 to the 5th joules. Our final kinetic energy is the velocity we just found of the two cars, so the mass of both cars together is 40,000. So our final kinetic energy is 1/2 times 40,000, 3.1 squared, 1/2 mv squared, and that's 1.9 times 10 to the 5th. So it's not conserved. It's like almost half, right?
Yeah, pretty much.
So how much energy was lost? How do we find that? We subtract the two. Okay. And we get 1.2 times 10 to the 5th joules of energy were lost. We're not conserved. All right. So we have a shopping cart. A 55 kilogram shopping cart travels at 3 meters per second to the right, to the left, I guess. And a 19 kilogram child moving at 5 meters per second to the right jumps onto the cart. Find the final velocity. What type of collision is this?
Perfectly. No, it's not perfectly inelastic.
It is perfectly inelastic because they come together. If he falls off and smashes his head, then it's not perfect.
Perfectly inelastic, right?
That's, perfectly.
I was saying not perfectly elastic.
Yeah, not perfectly elastic, perfectly inelastic.
Perfectly inelastic.
All right, good. So here's initial momentums. We have a little kid has momentum.
Wait, so it's not perfectly elastic.
It's
perfectly inelastic.
perfectly inelastic.
All right.
Which is like saying not perfectly elastic.
Yeah, that's what I was trying to get at. I was confused.
So we have mass and velocity plus mass and velocity. This time, both objects have momentum. Both have a velocity. And then we have them coming together, so we have one mass that has a velocity. So we have the kid, 19 times 5. And then we have the cart is 3 meters per second in the opposite direction. To the left, we say is negative for our coordinate system we're using. And our final mass is the little kid in the cart. So 55 plus 19 is 74. We're looking for this final velocity. So these two are equal to each other. We divide this side by 74. We add all that up and multiply and divide that by 74. And we get, yeah?
That actually doesn't equal 74. It equals 70.
55 plus 19.
Wait, what? You have to multiply first.
This is oh, you mean this right here?
Yep.
We're looking for V. This is PF, which is mass times velocity of the little kid in the cart. So he's 19, and the cart's 55. 19 plus 55 is 74. We don't know the velocity.
Well, wait, so what's going on with the...
This is all of this information.
Yeah, what's going on with
This is the kid, mass times velocity. This is the cart, 55 times the negative. Our PI is equal to our PF. Because of that, we can determine that, what was this answer? 19 times 5 plus 55.
Oh, I see what you're doing.
So now I divide this side by 74. I divide this side right here, John.
I got it.
By 74.
I thought you were supposed to do that whole thing and then it's equal to that, but you're doing 74 VF.
Yep. So there you go.
There you go.
All right, go on. Next, boom, bang. All right, so here's hand carts. A and B are on train tracks. A with a passenger that's 185 and moves at 3.5 meters per second. B with a passenger that has 150 kilograms and moves at 2 meters per second. B starts out at 15 meters ahead of A. So here's a little guy waving, hello, I love you, and he's traveling at 3.5 meters per second. Here's a little guy that says beat it. He's going away from him, but unfortunately only at 2 meters per second, which is slower than 3.5 meters per second. So distance between the two as this comedy starts is 15 meters. How long before A catches B? What are we going to do? How do we do this?
You have to find the acceleration of this. Wait, if it, and move that 3. It's constant, so.
This is 3.5 meters per second. This is 2 meters per second. The difference between the two is 1.5 meters.
So just 15 divided by 1.5.
There you go, bada bing. All right, 10 seconds. Yeah?
Yeah, you're good.
All right, how far do A and B go in this time? All right, we have 3.5 meters per second for 10 seconds. Takes him 35 meters. Just for A.
A goes through.
Now we're looking for B. B's traveling at 2 meters per second for 10 seconds.
20 meters.
20 meters, good. Got it? Yep, bing, bing. All right, what percent of the initial K is lost if they couple together when they come in contact?
So that's a perfectly inelastic.
Yep, they couple perfectly inelastic. So here we have this guy has his momentum, mass times velocity before. This guy has his mass times velocity before. When they smash together, well, we know what the mass of the two of them is. That's 185 plus 150 is 335. So all of this is initial, and all of this is after. This plus this equals this times that.
So divide that by.
And we're looking for this. So we this times this plus this times this. Divide by that. You got a momentum before and a momentum after. All right. So throw that in there. This is equal to that. Cross out. So we get an answer of 2.83 meters per second for our final velocity of the two together. That's only half the problem because we want to know what percentage of kinetic energy is lost, and we need to know the velocity because that's 1/2 mv squared. So we had to find the velocity using momentum because momentum is conserved, so we can do this. Now that we know what
to find out the kinetic energy for.
Yeah, so our initial kinetic energy is the kinetic energy of this guy,
and that's
1/2 mv squared, plus
velocity squared or something like that.
Yep. Plus the kinetic energy of this guy, 1/2 mv squared. That's all our energy that exists before they come together. And then our we have a mass and a velocity now. So after our collision, it's just 1/2 mv squared of this stuff. And we find the answer of this is 1,433 joules. This is 1,341 joules. We want to know what percentage. How do we find percentage?
Well, we'll subtract. Wait. Get to. Yeah, you just. Well, I can do that in my calculator.
Boom.
Like that.
So you subtract how much is lost, divide by what you had, times 100,